Good afternoon, everybody. Good afternoon. I knew this wasn't really a reticent crowd. You small and mighty, and appreciate the support here. I'm Andy McElroy. I lead Sandia's California site here, which if you kind of peer past the grapevines, you can see it over the edge. You're our friends, and so we did not invite you to our site. It's hard to get on our site. It's a logistical challenge, so we invite our friends nice places, not to our site, which is just right here, but you can enjoy the Livermore environment for those of you coming from other areas, the wineries. It's a beautiful place to be. This is our 4th annual Research Slam, and we're going to be later presenting the all-important trophy, which John Sorrow, the SLAC director, and I were lamenting that all of the winners so far have begun with L. Lawrence something. So we're just rooting for an S to start the winner this year. It could be SLAC. It could be. So thank you all for coming, for participating. We're looking forward to a really exciting day here. It's a lot of fun. We've got 4 great judges here sitting at the table with me. Pat Falcone from Lawrence Livermore, John Sorrow from SLAC, and Mike Witherall from LBL. And this year we're going to have a little different emceeing. We're going to have some of our former presenters do the emceeing. So I'm going to get off the stage and let them take over.
All right, good afternoon, everybody. Welcome here. We're all very excited to have you here at Garre's Vineyard and Winery in Livermore. For those of you joining us online, thank you for joining us as well. And to this year's Bay Area Research Slam, we're beyond excited to have you with us.
So before we get started, let's just go over what we're about to see. We have 12 amazing finalists from Lawrence Livermore, Lawrence Berkeley, Sandia, and SLAC, who all present a 3-minute story about their research with the benefit of 1 slide and 1 walk-up song. Our timekeeper will keep an eye on the time, so you just have to give these brilliant presenters your full attention. In between each finalist presentation, it'll be your turn to participate when we have some trivia questions related to the research you'll just have heard about, and then you can win a prize for a correct answer. At the end, you, as the audience, will have the opportunity to vote for your favorite finalist for the People's Choice Award. Following this, our judges will deliberate, and you can stick around for refreshments, and we hope to have the announcement of the winners around 5 p.m.
Of course, we want to share our excitement on social media, right? So before we move on, I just want to remind everyone to join the online conversation. If you're having a great time here in the event, please make sure you have your favorite moments on social media, And the hashtags are Bay Area Slam 2024. Don't forget your lab colleagues and also your friends. We are looking forward to see your posts.
Okay, so what's up for grabs today? Each finalist here has already received an award from the home institution. For this competition, however, though, the winner gets major bragging rights for being the penultimate 2024 slammer. There will be a 1st place, a 2nd place, and a 3rd place. There will be a People's Choice Award where the audience gets to choose. And the Bars Trophy we have right up front. So this is a team award that will go to the lab with the highest cumulative score of all their 3 participants.
And so, after our distinguished dozen give their talks, you will have a chance to vote. For our in-person audience, there are QR codes scattered around the room, which will take you eventually to the voting page. And of course, there'll be a QR code on the screen as well that takes you directly to voting. A link will be posted in the chat for those online to also cast their votes for their favorite participant. The poll will only be open for about 10 minutes, so please be sure to cast your vote as soon as the link is posted. And please wait until you hear all of the talks before you cast your vote or vote for SLAC at the beginning.
Okay, so this is a competition. And how will our contestants be judged, actually? So the esteemed panel of judges will be judging the contestants over several things listed out here, including technical content and clarity of the presentation, also the stage presence, the enthusiasm presenting their work in less than 3 minutes. Points will be deducted if they go over 3 minutes, and that's why we have our timekeeper. So who has the hardest job tonight?
We're very grateful to the panel of judges we have for this 2024 Bay Area Research Slam. And I know they've been briefly introduced, but I'm going to do it again, and otherwise I'd have to deviate from what I plan to say. So I want to take a moment to introduce each judge, and then I ask that each judge can stand up and just wave to the crowd as we acknowledge them. Patricia Falcone is the Deputy Director for Science and Technology at Lawrence Livermore National Laboratory.
John Sorrow is SLAC National Accelerator Laboratory's 6th Lab Director.
Andy McRoy is the Associate Lab Director for Sandia National Lab, Livermore, California.
And from Berkeley Lab, we have our lab director, Mike Witherell.
All right, so the good news is these judges are bribable. They've actually told me the bribes just have to be in the form of a 3-minute talk about work done at a national lab with 1 slide and some walk-up music.
Okay, before we move on, we want to give a big shout out to the Sandia Lab for putting together this wonderful event. But we do enjoy friendly competition, so please go ahead and cheer your favorite contestants. After all, they are all already champions of your respective lab slam. Now let's get this 2024 Bay Area Research Slam started. Our first finalist for this event, representing Sandia, please give it up for Jihoon Yang. From Bioresource and Environmental Security with a talk on who took art treasure.
Okay, yeah, most of us have the similar experience and memories of hiding my own treasure in the secret box. It could have been the coins or even the favorite food. At that time, we thought for days about what if someone took it and my mother would know about this place? Even for the personal treasure, we did it. Then what about the treasure of humanity? I believe the hydrogen gas is the treasure that will meet our future energy demand. The hydrogen gas is expected to the fossil fuels as an energy source by 2050. And its use is effective in reducing greenhouse gas that accelerate the climate change. Our society had tried to establish the underground hydrogen gas storage method to store a large quantity of them more safely. However, recent studies showed that we are losing almost 20% of our treasure by bacteria in the environment. So what should we do? It is necessary to understand the microbial community activities before storing the hydrogen gas. I collected the samples from facilities that is expected to be used as hydrogen gas storage in the near future. The gas composition in the pipeline was analyzed to understand what happens here. And the microbial community composition and the metabolic pathway was analyzed to understand who did it and how. From the gas composition analysis, I found more than 80% of gas in the pipeline was methane gas. Yeah, we don't know yet if it is produced by bacteria, but one thing is very clear. While we are trying to reduce the greenhouse gas above ground, the methane was accumulating underground. So the microbial community composition and metabolic pathway analysis provided the evidence to explain this situation. There were more methane-producing bacteria in these samples than other environmental samples, and they were highly related to the functions utilizing the hydrogen gas to produce methane and hydrogen sulfide gas. This could have serious implications for both our energy demand and the safety of our infrastructure. So through my study, I identified the hydrogen-loving methane-producing bacteria in the actual environment, but this is the first step to the national energy security. So my next step will control their activities using eco-friendly and also sustainable ways to better protect our treasure. Thank you.
Thank you, Ji-hoon, for getting us started. And now we will have our first trivia question. What is a greenhouse gas among the following? Is it A, oxygen, B, helium, C, methane, or D, argon? Yeah, on the right, yeah, sure. And the answer is C, methane, that's correct. And please participate in the trivia, there are prizes.
We should just prepare you, not all the trivia questions are going to be as easy, so make sure to pay attention. We just started you off with an easy one.
It wouldn't be science if there wasn't a quiz. All right. And so now, representing SLAC, our first speaker is coming from the Energy Sciences and the LCLS Directorate, Sandra Bavale, who's going to be giving us her talk about lights, camera, and electrons.
We're going to explore a hidden world. It's the world of electrons moving inside molecules. Did you just see that? And there, it's happening again. Can you see all of that? No? Well, even though it's happening all the time and everywhere, what I'm talking about is just too small and way too fast for us to see. First, let's talk about its size. Electron motion happens on the scale of atom. It's like trying to see something 1,000,000 times smaller than a grain of sand. But then electrons are also really fast. We're talking timescales of attoseconds, 10 to the minus 18 seconds. I know, it's hard to picture. But to give you an idea, when I blink, it takes about 1/3 of a second. And in that time, more than 1 billion attoseconds have already passed. And my job is to measure that. I mean, have you ever tried to measure something that you cannot even see? Well, it's very challenging, but it's also so exciting. I get to use an X-ray-free electron laser. Oh, it's just a small tool. No, I'm joking. It's a gigantic machine, 2 miles long laser, and it's right there at SLAC. It gives me ultra-short pulses of light. I send them on molecule, and bam, it takes a picture. But here's the challenge. In order to observe the motion, I need to compare pictures taken at different times. And to do that, I need 2 pulses of light, one to launch the action and one to take the picture. In 2018, SLAC became the very first place in the world to produce isolated attosecond X-ray pulse. And this was years of hard work. But you know what's harder? Getting 2 of them. Even harder, try controlling the super short delay between these 2 pulses. But it was a success. And now I can take many pictures at many different times and recreate the movie of how electron moves inside molecule. But why is that important, actually? Well, electron motion is the fundamental of everything. Me speaking to you today is possible because electrons carry information from my brain to my muscle. You watching me on Zoom or WebEx, it's also possible because the sound and image are transmitted through electrons that are moving in some circuits. Or if you're not convinced, how about more modern technologies like semiconductors? Did you know they heavily rely on controlling electron motion through material? And I work so that we understand all of that. Now, I know this was fast, 3 minutes, but compared to the electron motion I study, 3 minutes is practically eternity. Thank you.
Thank you, Sandra. As promised, we're going to do trivia again, and I hope it's not going to be so easy this time. So what is the natural time scale of electron motion? Is it A, 1 second? Is it B, 1/3 of a second? Is it C, 1,000,000 times smaller than a second? Or is it 1,000,000,000,000 times smaller than a second? That was a hand super fast with a big finger too. Was it what? What was it? D as in David, 1,000,000,000,000 times smaller than a second? Is that correct? Yes. Yeah. Well done. What do we have for prizes, actually? I'm curious. Let me see. All right. Okay, next up, representing Lawrence Berkeley National Lab, please give it up for Lisa Schlüter from Physical Sciences with her talk on why our universe should not exist.
You, your pet, and your favorite TV show should not exist. Actually, our whole universe should not exist. We should have annihilated with antimatter. Sounds like science fiction, but antimatter actually exists. The world around you, including yourself, is made from particles. An antiparticle is something like the mirror image of a particle. It has the same mass, but the opposite charge. Once upon a time in the early universe, for every single particle existed an antiparticle counterpart. Sounds romantic, right? But there's drama. When a particle finds its antiparticle soulmate, they annihilate, releasing a large burst of energy. But wait, doesn't that mean that once all the particles and antiparticles had found each other, there should be nothing left, right? Just energy. Well, this is obviously not true. We are here, right? Let me tell you, we just stumbled upon one of the biggest questions in physics. Why the heck are we even here? And the answer is, we don't know. But in my research, I'm trying to figure that out. There has to be some process that created a few more particles than antiparticles. And these extra particles, they did not annihilate, they survived. And they make up the universe as we know it today. Our goal is to prove experimentally that such a process exists. And by us, I mean Berkeley Lab, as part of an international collaboration called LEGEND. We search for a special nuclear decay of an element called germanium. For the experts, I'm talking about the isotope 76 here. And if this decay exists, it would create 2 electrons and 0 antiparticles. And the discovery of this imbalance would be groundbreaking, because it would give us the key to solve the mystery of our existence. Unfortunately, we haven't measured this decay yet, because it is extremely rare. And that's why we are building a huge experiment using 1 ton of germanium. But still, if we let that sit for 5 years, we only expect that 2 nuclei will have decayed. And my daily job is to make sure that we don't miss these 2 decays. Now at the end, you still don't know why you exist, but hey, at least we're in this together and we have a chance to figure it out.
Thank you for making me think about the mystery of my existence while I'm still at work. We have another trivia question. How many nuclear decays without antimatter would we expect after letting 1 ton of germanium sit for 5 years? Is that 50, 11, 2, or none? And the hand in the back. Yes. Correct. So unfortunately, you will see we will need to stall for a little bit of time to let the judges work. Unfortunately for you, I'm not funny, so I'll mostly just be up here waiting. And now we're good. Okay. Our next finalist is representing Lawrence Livermore National Laboratory. Please give it up for Jillian McCool from Physical and Life Sciences for her talk, Racing for a Cure, Engineering Immune Cells for Improved Cancer Targeting.
Picture this, a future where cancer patients had fast and reliable treatment options, where families could find hope in therapy that not only effectively targeted the cancer, but mitigated the risks associated, where treatments were fast, affordable, and available almost instantly. While this may sound like a revolutionary idea, cancer researchers are already paving the way for new and improved treatment therapies. The downside is that these new treatments face significant challenges, from high cost to low patient safety to efficacy of the treatment overall. So today, researchers are turning their focus to new personalized types of cancer therapy called CAR T therapy. CAR T therapy works by altering a patient's immune cells outside of their body to better identify and attack cancer cells once back inside the body. These cells are traditionally better, faster, and stronger when it comes to targeting cancer. But the main problem with CAR T therapy is the high likelihood that this option will fail. Typically, between 30 and 40% of people who receive CAR T therapy don't fully recover from their cancer. And additionally, the trauma that can occur by putting altered immune cells into an already unhealthy body can be detrimental. So this is where my cancer therapy research drives into the race. My goal is to alter a specific receptor on the surface of these immune cells that allow them to better identify those cancerous conditions in the body. Think of this like changing the tires on your race car to better suit the conditions of the track. My approach differs from current CAR T therapy methods due to the biological relevancy of our engineering strategy. So think of it like this. In order to be faster than the competition, engineers might change the body of their race car for better aerodynamics. I tried to do something similar with my engineered immune cells. My research targets and delivers a specific cancer targeting molecule to these immune cells that's encompassed in a natural coating. Not only does this coating allow that cancer targeting molecule to stay stable, but it also allows these immune cells to continue to function as normally, something that current CAR T therapy methods just don't do. So, my cancer therapy research isn't just about transforming treatment options. It's about transforming lives. By harnessing the power of these biologically relevant engineering strategies, not only are we racing towards a cure for faster and safer treatment, but we're also decreasing side effects. Together, we can drive towards a cure, one engineered immune cell at a time.
Thank you, Jillian, for your talk. It's trivia time again. I hope it's a tough question because there are no multiple choice answers here. What type of cancer do current CAR T therapies target? If you just heard from her talk, you have the answer. Anyone? No? Then judges will have more time to judge it out. You guys can just think about. Yeah, here?
Is it all of them?
Unfortunately, no. I'll just wait until he gives me a heads up, and then I'll tell you the answer. I think you can guess it.
Yes.
Yeah?
Is it solid tumors?
No, I think so. Yeah, good to go. The answer is blood cancer. I'm excited to introduce our next finalist representing Sandia. Please give it up for Scott Monesmith. He's from Power Sources R&D with a stock cracking solid electrolytes using computer simulation to
So, I'm going to start this off by telling you guys maybe the most memorable time that my phone ran out of battery. So, I was running late for an event up in San Francisco, and I just dropped a pin really hastily to try to remember where I parked my car. And unfortunately, my phone ran out of juice just during the talk, during the presentation. And yeah, the way that worked out was, as we all do from time to time, I found myself just sprinting up and down those giant hills in Noe Valley, just trying to find it, frantically pushing the unlock button on my car keys. Was very, very perturbing to the neighbors there, and it was way more cardio than I'd budgeted for that night. So all this is to say that storing enough charge is an issue that affects many aspects of the energy storage industry, ranging from small consumer electronics, like your phone, to some massive gigawatt-scale batteries that are intended to store energy for America's electrical grid. Now, batteries are fundamentally chemistry in a can. The energy that they can sustain and output is limited by the energetics of the chemical reactions that take place inside them. If we want batteries that are smaller, lighter, and contain more energy, then we just need to use higher energy materials. Unfortunately, many of these high energy materials require a fundamental paradigm shift from a liquid-based system to a solid-based system. And as anyone who has handled these can tell you, they're extremely fragile. They rip, they tear, they puncture, they break, they crack. And this makes it difficult to actually implement them in real devices, and even makes it challenging to scale these up to a lab level to test out and prove out new concepts. Now, what's a lot easier is to use computational methods to simulate their behavior. What we do is we use what's called the phase field method to try to capture as much of the physics going on inside the battery as we possibly can, namely the electrochemistry and the growth of cracks. And we use that to kind of understand and project how we think the batteries will behave during operation and handling without actually needing to operate or handle the batteries in the real world. It's kind of like using a virtual lab instead of a real one to try to test out these new concepts. Now, this skirts around some of the inherent limitations of hands-on laboratory work in that it's far cheaper, both in terms of money and in time. In fact, we can run thousands of simulations in the same amount of time that it would do to take just one single laboratory experiment and requires only some modest computational resources. Now, I'm not trying to suggest that we're trying to supplant the role of experimentalists. No one's coming for your jobs anytime soon, I promise. But I view this as a complement to experimental work. If we can help them by screening some materials, say we try 100 and 95 of them are duds right off the bat, then we can save them an enormous amount of time in going from initial concepts to actual viable prototypes. So this synergy is what I view as the best way to do battery materials design, enabling more electric car miles, more charge on your phone, and a cleaner, more secure energy future. Thank you.
Thank you, Scott. I'm glad to know that the theorists aren't going to be, or the computers aren't going to be coming for my jobs. And so with that, we're on to the next trivia question, which is, which of the following is the best approach to battery materials design? Is it A, physics-based computer simulations, B, iteratively test different batteries in the laboratory, C, ask ChatGPT, or D, laboratory investigation complemented and informed by computer simulation? And I think that hand went up first. Sorry, which one?
Option D for David.
D for David is correct. And with that, our next speaker is Chang Peng, coming from the SLAC National Accelerator Lab Energy Sciences Directorate, and she's going to tell us about her daily adventures in the life as a computational condensed matter.
Now imagine this. A new day begins with reading an exciting email from your colleague. His latest experiment might uncover a completely new phase of matter, something no one has ever seen before. Think about a celebration? Of course not. So as a theoretical physicist, my job is to figure out why this can happen, and that's where my work begins. Experiments can be extremely expensive. At SLAC, a single experiment can cost as much as $1 million. So scientists are always looking for ways to reduce the cost and increase the chances of success. That's where theory becomes handy. By making predictions and explaining unexpected results from experiments, theorists can help experimentalists make sense of their research with fewer experiments. My role is to build models, or what you may call digital twins of the materials you are studying. With the digital twins, I can make any necessary tweaks or adjustments. And do you know the best part? All that I need is a computer with internet access. My research is in computational condensed matter physics, which involves studying tiny subjects like electrons, atoms, molecules, solids that form the condensed states. But modeling their behaviors isn't easy. Think about that. If I want to understand how graphene becomes a superconductor, can I just throw a graphene into my computer and expect it can figure things out on its own? No, no, no. What I do is to encode the material into an equivalent problem using programming languages. That is what I call a model. This model has to follow some basic rules. If I want to understand electron behaviors, then the model has to follow the quantum mechanisms. But you may not realize it. A tiny crystal, no bigger than your fingernail, can hold an unbelievable amount of electrons that modeling them on a single computer is impossible. So I have to rely on large-scale computing clusters to get the job done. Most of my day involves sitting at my computer, writing code, uploading jobs, downloading data, analyzing the model's behavior, and draw the conclusion for the materials. There are so many fascinating problems remain unsolved in the condensed matter physics. So our theorists work not only advancing the understanding of the new materials, but also impact our future. Thank you.
Thank you, Chang. Okay, that's a hard one, for me at least. I had to ask Ben if every little detail mentioned in the question is important, but apparently it is. So, simulations of quantum states can require vast amounts of memory due to the exponential growth with each additional particle. Approximately how much memory, in terms of order of magnitude, is needed to store the complete quantum state of 64 fully entangled spin half fermions, oh my God, using double precision floating point numbers? Whew. Is it A, terabytes? Is it exabytes? Is it C, zettabytes? Or is it D, yottabytes? Any idea, anybody? A hunch somewhere in the audience. Yeah. Bernard? It is not yottabytes. You just increase the chances for everybody else. It's good. Any other guesses? Yes. No, it's not C either. I'm very sorry. Okay, 50-50 chances now. Come on. Yeah, somebody flip a coin. Exactly. That's a scientific approach. We'll take it. In the back, yes. Is it B exabytes? I think you're right. It's B exabytes. Yes. Okay, coming up next for Lawrence Berkeley National Lab, please give it up for Gurthud Sethi from Energy Sciences. He is drawing an inspiration from plants with his excitonic superfluid.
Have you ever been around plants and felt inspired? Well, plants are truly inspiring. They convert carbon dioxide into oxygen using sunlight. Not just that, plants incredibly utilize 100% of the energy they absorb from the sun, while a typical modern-day solar panel utilizes only 20% of the absorbed energy. Wonder why? Actually, the light absorption process in plants involved the creation of a positive and a negative charge bound together. This pair of opposite charges is called an exciton. You can think of it as little energy-capturing entity that forms by absorbing energy from the sun and then transports the absorbed energy to the reaction site, where carbon dioxide is converted into oxygen. This transport of energy is highly efficient with minimal losses. It's almost like a perfect food delivery service that delivers hot food like it just came out of the kitchen. There's no heat loss during delivery. Unfortunately, in the material used currently in the solar panel, this food is way too cold by the time it reaches its destination. In other words, the energy transport is highly inefficient. Imagine having a material that can harness energy from the sun with an efficiency comparable to plants. That would cause a huge dent on the impending energy crisis. At Berkeley Lab, we have discovered a new material, a carbon-based material that allows energy transport using excitons with absolutely zero energy waste. Using computer simulations and supporting experimental evidences, we have shown that there's a unique arrangement of atoms inside this material that allows excitons to not just flow, but superflow. And when I say superflow, I don't mean speed. I mean the flow of excitons with absolutely zero resistive loss. That is, the energy transport is 100% efficient. And this is guaranteed by the quantum mechanical nature of this material. In fact, materials that can do this are called excitonic superfluids. They were theorized in 1960s, but so far, there are only about 10 known candidates in the world, and one of them is this material we discovered at Berkeley Lab. But it comes with a challenge. It's only at low temperatures that excitons superflow in this material. We're working to raise this temperature, possibly reach ambient conditions. Once that happens, this material can have applications going beyond solar power generation in areas like effective laser design or targeted radiation treatments. Possibilities are limitless. So really, next time when you are on plants, I hope you feel truly inspired.
All right, we have another trivia question for you. When were excitonic superfluids first theorized? Is this the 1940s, the 1960s, 2001, or 3 months ago? The guy with the bat. Yes, that is correct. All right, I actually wrote a joke for this. No, I'm just kidding. I'm not going to do that. Yeah, maybe I should have, actually. You guys want to hear about compressible mixture theory? All right. Our next finalist is from Lawrence Livermore National Laboratory. Please give it up for Casper Donison from Physical and Life Sciences, who will be talking about agriculture and solar power, an unlikely alliance.
Buy land. They're not making any more. These words, attributed to Mark Twain, capture a great challenge of our time. How should we use our finite resource of land? The landscapes of today are very different from Mark Twain's era. In fact, there's a battle taking place across this country between the rural communities and renewable energy developers over the use of farmland for solar power. In the last 5 years, 1/3 of solar power projects have been cancelled and half have been delayed by 6 months or more. The leading cause has been pushback from farmers and rural communities. Now consider the implications of this for the US government's goal of achieving 100% clean power by 2035. We're not yet at 50% clean power, and our demand continues to rise. If we're going to balance these competing demands of land, we need to use land differently. And here's one way that we can. With agrivoltaics, or dual-use solar, a new model that integrates solar panels with the farming landscape. Panels are elevated high to create space underneath for crops and livestock. Panels are spaced further apart to give room for farm machinery and for nature. These projects are starting to be developed across this country, and it's important we understand how they're being received. My research explores the public discussion and public sentiment of these projects to help policymakers increase adoption rates. And to do this, I've analyzed and coded hundreds of local newspaper articles in the areas where the projects are being developed. I found that farmers are supportive. They see agrivoltaics as a win-win. It increases their income and allows them to continue their traditional farm practices. In hot western states, agrivoltaics are seen as positive because they can shield from the beating sun the farm workers and crops that are underneath. In fact, in California and Colorado, farmers are finding that agrivoltaics can increase both the crop yield and the renewable energy generation. That's a rare example of 1 + 1 equaling greater than 2. Now, it's not all positive. We need to consider other views as well. And in the more populated eastern states, there's still a concern about the visual impact of seeing agrivoltaics on the landscape, and a concern that not all forms of agriculture may integrate well with these panels. So we need to consider that going forward. Mark Twain may have been right. We can't create more land, but we can change how we use it. And agrivoltaics may be one change that can bring together two warring communities, increase the adoption rate of solar power projects, and deliver us that clean energy future.
Thanks, Casper. It's really an inspiring talk. Trivia time. And the next question is, yes, you have multiple choice here. California has the greatest installed solar capacity in the US. Which state has the second greatest installed capacity? A, Texas, B, Arizona, C, Florida, D, North Carolina. I think, yeah. Someone raised a hand, right? Yeah, that's the correct answer. I think we finished this pretty fast. I think I have to wait. Yeah, it's done. Now, representing Sandia, please give it up for Michael Level from Materials Chemistry. His talk on repurposing natural gas infrastructure for green hydrogen transit.
As the season turns to fall, we're going to be seeing a lot more of these pretty blue flames. For cooking, for pumpkin spice lattes, for keeping the house cozy and warm. But have you thought about sustainability? Every time your stove or heater lights up, it's burning natural gas, a fossil fuel releasing carbon into the atmosphere. It's so convenient and reliable that we rarely think about how dependent we are on it. In fact, the US burns 30 trillion cubic feet of natural gas each year. That's 35% of our energy-related CO2 emissions. So what if we could keep that convenience, but ditch the carbon? Enter green hydrogen, a zero-carbon fuel produced from splitting water. And we may be able to blend hydrogen with natural gas and use our existing gas pipes to deliver it, cutting emissions and driving the hydrogen economy forward. The challenge? Well, at the molecular level, hydrogen is quite different from natural gas. So we need to be sure that our pipes can handle it safely and reliably. This is where my work comes in at Sandia National Labs. Now we know that hydrogen can embrittle metal pipes, but its impacts on plastics is less understood, especially polyethylene, which makes up millions of miles of gas lines in the US. Some studies show that hydrogen causes cracking, while others suggest that it actually strengthens the plastic. There's a big knowledge gap there. To solve this, I'm developing ways to study the microscopic structure of these polymers. Using advanced light scattering techniques, including lasers and X-rays at the SLAC synchrotron, I examined the molecular vibrations and crystal structure of polymers exposed to hydrogen and blended gas environments. So some days I'm taking pipes, cutting them up, and putting them into hydrogen, and completing experiments that simply have never been done before. Others, I'm figuring out how to use traditional scientific instruments, but with hydrogen. Good news. After 1 week of exposure at different pipeline pressures, my tests show that hydrogen does not permanently damage polyethylene, a promising sign. However, we need more long-term data. And moving forward, I'll be developing new ways to study how hydrogen interacts with our infrastructure. Finally, understanding how hydrogen interacts with materials has far-reaching impacts, including other applications. In just a few years, we could be driving to visit family in hydrogen-powered vehicles, towards a holiday season warmed by hydrogen, and baking hydrogen cookies, all while combating climate change. So, whether you're humming carols or rocking to Metallica, let's take this step towards greener homes and a sustainable future.
Thank you, Michael, for your talk. And now it's once again trivia time. And so the question is, what material is widely used in US gas pipelines and is being studied for its interactions with hydrogen? Is it A, iron, B, polypropylene, C, polyethylene, or D, steel? Yeah, in the back. Sorry, what was that? C, polyethylene? C, polyethylene is correct. And I don't even have to stall for time. Our next speaker coming from SLAC is Tianzi Zhu, who represents the Accelerator Directorate at SLAC, and he's going to be telling us about how he takes atomic close-ups using a zoom lens for ultra-fast electron camera.
Imagine you're at a party, holding your camera, trying to capture a perfect shot of all the epic moments. Everyone is dancing and moving around, and somehow all your photos just come out so blurry as if you're already drunk. Well, turns out that your camera is just not fast enough. Now, think about capturing something much faster, not just people dancing, but atoms and molecules moving at lightning speed during chemical reaction. How can we possibly see their motions? At SLAC, we use a particle accelerator to generate ultra-short pulses of electron beams, each lasting just tens of femtoseconds. That's a tiny fraction of a second. By sending these electron beams through the sample and analyzing how they scatter, we can visualize the atomic dynamics of physical or chemical processes as if everything happens in slow motion. Now the party is in full swing, and you've got a new fast camera in hand, ready to capture the best and funniest moments. Wait, what is that fire thing on top of the table? Oh, it's your friend's cat yawning. Hurry, let's take a picture. You take out your camera, but now you've got a different problem. You're standing across the room, and the kitty just looks tiny in the picture. Sometimes we face similar issues with our electron cameras, where some of the feature we want to resolve is too small on detector. Seeing those features more clearly help us understand the properties of the sample so we can create new material state that could be useful for next generation electronic devices. To do that, a fast camera alone isn't enough. We also want a closer view with higher resolution. And this is where my research comes in. I'm working to improve the resolution of our ultra-fast electron camera with powerful magnetic lenses. Just like zoom lens on optical cameras, magnetic lenses magnify the electron beams so we can see the snapshots in fine details. One challenge with our electron beams is that they have much higher energy than the ones in typical electron microscopes, making it harder to focus and magnify. I have developed a lens system using permanent magnets. similar to the ones you find on your refrigerator, but with their material and geometry chosen to produce a much stronger magnetic field. These permanent magnets can provide strong focusing and high magnification for electron beams. Plus, they're super compact and can easily fit into our system. Using these magnets as zoom lenses, our electron camera can combine the lightning-fast speed with crystal clear vision, allowing us to capture snapshots of atomic dynamics with incredible precision. Thank you.
Thank you, Chancy. All right, they gave me the hard slack questions. Don't give physics questions to a biologist. All right, the wavelength of electrons in SLAC's ultra-fast electron camera is extremely small. How does it compare with the size of an atom? Is it A, about the size of an atom? Is it 1/10 of the size of an atom? Is it 100th of the size of an atom, or is it 1,000th of the size of an atom? Okay, it's not just me. Good, good. Makes me feel better. Yes. We have D, 1,000th size of the atom. Is that correct? I think. Yes, it is. Next up, representing Lawrence Berkeley National Lab, is Yumari Vasquez from Biosciences. She is going viral, literally, with her giant virus edition. The floor is yours.
Has anyone here ever gone viral? Maybe it was a hilarious tweet, a TikTok challenge, or, dare I say it, a Macarena dance video. But what if I told you about something that hasn't hit your social media feeds yet, even though it's been going viral for millions of years? Let's talk about giant viruses. Giant viruses are much larger than the typical tiny troublemakers you're probably thinking about right now. 100 times larger than the virus that causes COVID. And get this, giant viruses are found everywhere, in water, in air, in soil, even in your own gut. The giant viruses I'm studying don't infect humans. In fact, they could be the key to finding new ways to clean up the environment or even fight pathogens. For example, you may be familiar with harmful algal blooms, which can ruin your family vacation faster than an embarrassing photo and devastate aquatic ecosystems. Giant viruses infect the algae responsible for these blooms and stop them before they grow out of control. It's not just algae. They can infect and eliminate brain-eating amoeba in the environment. Sounds like the kind of viral sensation we should all be seeing on our social media feeds, right? Yet, for many of you here, this is probably the first time you've ever heard of them. That's because giant viruses were only discovered 20 years ago. Thanks to advancements in metagenomics, the process of sequencing DNA from the environment, we can finally give these fascinating viruses the research attention they deserve. My goal is to identify new genes in giant viruses not found in any other organisms, so we can better understand their unique biology. These genes could reveal how they got so big and how they're able to infect different organisms. My approach is to use metagenomics and computational tools to analyze thousands of viral genomes, and it's working. I'm not finding a few new genes. I'm talking about hundreds of genes never seen before. Genes I believe could lead to targeted, environmentally friendly ways to control algae or brain-eating amoeba, so that your next family vacation is picture perfect. I'm on a mission to make giant viruses go viral beyond the lab. So I want all of you here to help me spread the word out about these incredible giants. Let's make giant viruses the next viral sensation, because they could lead us to the next big scientific breakthrough. And who wouldn't want to go viral for that?
Thank you. The last worldwide viral sensation made me defend my PhD on Zoom, so. All right, we have a question here. The next trivia question is, some giant viruses are known to be as big as what? A bacterium, a red blood cell, a grain of rice, or a Lawrence Berkeley turkey? And this is a great set here because I'm not confident I could put these in size order. Anybody have a guess? I think we can rule that one out. Yes. No. We're now down to 50-50 shot here, so. Yes. Correct. Our next finalist is from Lawrence Livermore National Laboratory. Please give it up for Nicholas Cross from engineering, who will be looking inside batteries to predict failure.
The world is becoming electrified, which means that batteries are everywhere. They've been in your phones and laptops for some time now. Many new cars are powered by them, and soon they may even be powering airplanes. But batteries have this little problem. They are difficult, if not impossible, to take apart, diagnose and repair any issues, and put back together again. Think about it. If you have a bad battery, no one says, oh yeah, let's take a look inside. They say, toss it in the trash and just get a new one. So as scientists, we need to be able to predict when batteries will fail and understand the mechanisms that cause that failure. In lithium metal batteries, one form of failure is the formation of what are called dendrites. So dendrites are these little tendrils that reach out from the electrode surface, scavenging for lithium. But if they reach out too far, they will touch the opposite electrode and cause the battery to short circuit and maybe even catch fire. And our predictions on when dendrites will form don't align well with the experimental data on when they actually occur. So my job is to build numerical models to improve our ability to predict dendrite formation. And I have found that the key is in the solid electrolyte interphase, or SEI, which is this nanometer thin film the size of a few strands of DNA that covers the battery electrode and slowly grows as the battery is used. And the SEI is dense, which means that lithium has a really hard time diffusing through it to get to the electrode surface. And this slow transport can cause dendrites. So I have found that if we include a growing SEI into our model, we can more accurately predict when dendrites will form. But how we include it is important. There are ways that we can do so such that the model agrees with their experimental results on when dendrites form, but completely contradicts the published literature on how we have seen the SEI grow. So I'm working with my computational and experimental colleagues to build a model that both accurately predicts when dendrites form and agrees with how we know the SEI grows over time. So as a result, we are learning how to better engineer materials and better operate our batteries to control solid electrolyte interphase growth and prevent dendrites as a form of catastrophic failure in the next generation of batteries. This will enable your electric planes, trains, and automobiles to go farther and charge faster. And fewer batteries will be thrown in the trash.
Thank you, Nicholas. The last trivia question for this event. What country recently announced that the number of battery electric vehicles has suppressed the number of gas-powered vehicles on the roads? Unfortunately, there are no multiple choice here. These questions are distributed by LLNL. Yeah, so they didn't give a chance to give us the multiple choice. So, anyone? You're from LLNL, I know that. I remember you from the last base lab. Yes. Any other guess? I hear some whispering there. Someone is cheating, I guess. Yeah? No, sorry. Yeah, correct.
Okay, at this time, I'd like to ask all our finalists to come back up on the stage for a final bow and then a photo.
All right, and so now with that, it's time for our judges and our audience to do their civic duty and vote. For the in-person audience, like I said before, there are QR codes distributed around the room, and I hope that this screen will get turned back on. Oh, it's happening. Which will have a QR code to take people to vote for their favorite candidates. For people watching online, the link to the QR code, or the link to the voting website should be in the chat right now. The poll will be open for about 10 minutes. And so please be sure to cast your vote for your favorite participant. Oh. So this one, or yeah, either one of them will eventually take you to the voting page. I think you have to navigate through the website to the voting page. But that one's easier. Just use that one.
Is it still 5 o'clock? All right.
Oh, sorry, there's a question?
Go ahead. Is there a Wi-Fi password? All right. Right. While everybody's super busy voting, I love to see that. Thank you.
First lap.
We are. No, I mean, LBL has brought home the trophy twice. Come on, we can triple it. So in my script, we're apparently ahead of time, so it won't be, you won't have to wait until 5 p.m. for the winners to be announced. It's about 10, 15 minutes, I guess. They're going to be announced on the website and on social media for those in the virtual audience. And yeah, while our judges will deliberate, I don't know if they have to deliberate anyways. They have a tough decision to make, though. There's refreshments waiting, I was told. Is that still true? Is that holding true? Yeah? Okay. So there are refreshments waiting for everybody. And I'm sure you'll have plenty to talk about all the amazing science that we heard from our 12 fantastic scientists and finalists. And it's time for a break. And with that, I'll send you off into break time, and please enjoy refreshments.
All right. After a lot of deliberation, our judges have made their decisions, so we're going to be going through the awards. And before we get started, don't read anything into which one of us is announcing. We decided beforehand, so we didn't have to decide, are we doing our lab or are we not? So this is predetermined. The People's Choice Award goes to Michael Lovell of Sandia for
The third place goes to Casper.
And our second place winner is Yumari Vasquez.
All right, so first place goes to Nicholas Cross from Lawrence Livermore National Lab.
Congrats, well done.
All right, the last thing that we have is the lab trophy, which is right over here, and I assume one of these will be presenting it. And the overall winner of the lab competition is Lawrence Livermore.
In under 3 minutes.
Congratulations to everyone. Before we conclude, we'd like to take a moment to thank the organizing committee for making this event possible. There were a number of people involved behind the scenes to make sure everything you heard and saw today runs smoothly. Their hard work and dedication have helped bring us all together to celebrate this event. We truly appreciate their efforts and commitment to the success of the Slam. A huge and heartfelt thank you for everyone here. Thanks all for joining us and also the virtual audience. Please stick around for the refreshments and see you all tomorrow. Sorry.